Hey guys, you're watching Python tutorial videos on my YouTube channel Python for Microscopists. I just returned from a trip where we conducted a few workshops and I started to realize that a lot of you, at least a lot of microscopists out there, are not aware of various digital filters, whether it is Gaussian filter, median filter. It almost appears that you guys are applying these filters hoping that, okay, one of these filters is gonna do the job. So I'm recording the next set of tutorial videos to explain what some of the most common filters are, what actually is digital image filtering. And in this tutorial, let's actually start by understanding what is image convolution, because this is the basis of any digital image processing, digital image filtering. So I know we talked about a lot about deep learning and everything, but again, I don't want you to think that deep learning, machine learnings, and all of this is magic, convolution, or whatever filters. Really, it's very important for you to understand. So I hope you watch these tutorials in their entirety to at least get a good understanding of what these filters are. You can eventually choose to use other advanced tools, but obviously you need to know what other, what these tools are supposed to do, so you can pick the appropriate one for the job. So let's jump in. And first, let's have a look at a quick digital image. Okay, so this is a H&E stained image. Of course, I converted this into a grayscale, but as you can see, okay, you see a whole bunch of cells or nuclei in this image. Now, if you zoom in, let's actually zoom into this region right there. And when you zoom in all the way, you start to see the pixelated image, right? So when you zoom in, you'll see these pixels, and this heart-shaped thing is actually right here. And as you can see, some of these pixels in here are darker and some less dark, and surrounded by some of these bright pixels. Okay, what does that mean? Well, this dark pixel may have a value of 0 and the bright pixel may have a value of 255, and somewhere in between the values between 0 to 255. Now, when again, I'm representing some of that as a 5 by 5 grid here. So the values are ranging from 0 to 255, as you can see. And that's because this is a representation of an 8-bit image. Now, whenever you perform any type of image convolution, or for example, if you apply a Gaussian filter onto a digital image, whether you use ImageJ or Python or any software to apply this, you define a kernel size, right? The kernel size can be 3 by 3 or 5 by 5. So you define typically a kernel size, no matter what digital filter you use. So in this example, I'm showing you a kernel of 3 by 3 with some random values between -2 to 2 here. So it's -1, 0, 1, and so on. So this is a 3 by 3 kernel. So when you apply a kernel onto an image, all it's doing is applying this. For example, this is a 3 by 3 grid, so it multiplies -1 with 170, okay, and then 0 with 245, and then 1 with 0, right? You keep doing this. This is not a matrix multiplication, as you probably learned in your high school math. In fact, this is a one-to-one multiplication. So this number here is multiplying with this number over there, and the 2 down here is multiplying with 234. Okay, so you're multiplying all of these and adding them. In this example, it results in a value of 394, which means the central pixel, because I'm applying this right here, right? So the central pixel value of 42 will be replaced by 394. So when you apply this kernel, the value changes, modifies. What about all of these other values? Well, now you move this kernel by 1 and then do the math again, and then move it again and do the math again, and so on. Okay, so when you do that again, the output image, as you can see here, the central pixel value is replaced by from 42 to 394. Okay, now you can move this by 1 to the right. Okay, this is called stride. If the stride is 1, that means it's just going to the next one and the next one and next one. By the way, you can move this entire window by 3 or by 5 times, and so on, and that defines your stride. Okay, and then typically you go from top left to bottom right. So that's pretty much it. So this is the convolution operation, and this is the basis of any digital image filtering. Whether you're doing deep learning or whether you're doing traditional Gaussian filtering or median and so on, this is exactly what's going on. You're actually applying a kernel, and there are many types of kernel. For example, if you want to perform Gaussian operation, then as the name suggests, Gaussian is nothing but a bell curve, right? In 2 dimensions, there is a peak in the middle, and then it tapers off as you go to the sides. Okay, so the value in the middle is the highest, and here it's somewhere in the middle, and over there it's very low. And by the way, I'm showing this kernel as 1 over 4, 1 over 8, 1 over 16, because when you add all of these values, it should equal to a value of 1, meaning I'm not changing information in my input image. So this is a normalized Gaussian kernel. Or you can basically, you could have started by a value of 1 here, a value of 16 in the middle, and so on. So again, a summary: convolution is nothing but this multiplication of a kernel with your original image, and you keep moving this window and doing this math all over your image, input image. Now, the shape of the kernel or the values that are inside the kernel defines exactly what type of operation you're performing. So when you actually, in your image processing software, when you select Gaussian, smoothing, or median, that's when you're defining the kernels. Okay, that's how you define the kernel. Now, what happens when you, for example, what happens with these values around the border, like 170, 234? How do I handle those? How do I multiply those, right? So when this stride actually goes all the way to the end, how do you deal with these edge values? Because there is nothing on the right hand side. So that's when we actually do something called padding. So to the image, you actually add, there are many ways of padding the image. So to the right and the bottom, you can actually add extra pixels with a specific value. In this case, my value is 0. Or you can basically say, okay, extend this by 1, except here, take whatever the value is of the one that's next to it. So you can replace this with 149, 160, 224. So there are many ways of padding and various built-in algorithms, in Python, for example, Gaussians or others, they'll let you choose what the padding is. But it's important for you to understand that something like this exists. If you don't pad the image, then your output image will always be smaller than the input image. So if I go back, so if you are not padding this image, then realistically, this specific image starts right here, right, at a value of 394, because there is nothing to do here, there is nothing to do over there, because there is no values on the left-hand side. Yeah. So uh, this is how you can actually keep your output image same as your input image, by padding. So I hope that makes sense. And finally, what are the best data types for image processing? And again, as you probably know, there are many ways of handling these numbers in Python or in any computer, basically, right? Typically, most of your images are probably unsigned integer 8, which means the values at every pixel range from 0 to 255. Okay, the example I just showed you here, these are all 8-bit, right? So 0 to 255. But what happens when you, for example, multiply 234 by 2? So the value will become 468, which is above, larger than 255. That means if you try to process an 8-bit image and try to save it as an 8-bit image, then some information is clipped. Or, so all the values above 255 would be equal to 255. That's what I meant to say here. Okay. Or what happens if you take this 234 and multiply by 1 over 8? If that's not divisible by 8, then you'll end up with a fractional value. And if you round it off, then you'll get a lot of rounding errors. So considering all of that, the best way to actually do math or to do any type of image processing is by converting your input image into a floating point image. So typically the values are between 0 to 1. So if your value is, instead of 128, if your value is 0.5, then you can do all types of math and still keep that the image information intact. So I recommend floating. I mean, unsigned integer 16 is also okay because you go from 0 to 65,535. But again, for example, if you use, I believe, scipy.image, it forces you to convert your images into floating point because most of these tools that are available in scipy.image, they work on floating point numbers. So keep that in mind. Okay, so now knowing this, again, how do you convert these? For example, in scipy.image, you can actually say in scipy.image, you can import image as float. Okay, so when you load an image, you can actually call image as float. So by importing, while you're importing, the image is automatically directly converted into a floating point. And of course, if you want to save it back as an image, like a JPEG or something else, you can always convert it back to UByte, which is 8-bit integer values, and then save them as your image files. Okay, so enough of this theory. Now let's actually get into the spider and write a couple of lines of code to understand this convolution between an input image and a kernel. So let me exit out of my PowerPoint, and here is the spider interface. So let's go ahead and import our image, which means let's use from skimage import IO. Again, there are many ways of importing images. You can use OpenCV. I've covered this in one of the previous tutorials. In fact, part of this tutorial has been already covered, but I'm after meeting quite a few of you in the field, I'm recording this again to reinforce this message. Okay, so let's assign a variable to our image, and let's do io.imread. And under images, I have an image called BSC 25 sigma. I added some noise to a BSC image, noisy.jpg. Okay, and let's go ahead and import this as gray. Okay, as gray equals to true. So now let me run this line to make sure everything is fine. Okay, there you go. My input image is a 8-bit unsigned integer, 714 by 901, and you can see the actual values over there. Okay, now like I said, the best way to deal with to do digital image processing is working with floating point numbers. So image as float, and then I can just do image as float right here. So now let's go ahead and run this again. And this is converted to float 64, and you can see my values are 0.15, 0.14, 0.07, so everything between 0 to 1 there. So now we have our input image ready. Let's actually define a kernel. So first of all, let's define a normalized box filter. What that means is it simply takes the average of all the pixels under the kernel area. That's it, okay? And replaces the central element with whatever that average is. Okay, so by the way, this is almost like a blur operation. Okay, so you're just blurring it by running a window on it. So let's actually create, well, actually, first of all, let's import NumPy. Okay, as np. So now that we have our numpy library, let's actually create a array of all ones. And how big is the array supposed to be? Let's actually create an array of 5 by 5 of all ones. Okay, now this is okay, but again, like I mentioned earlier, you always normalize this filter. Okay, so you always normalize it to make sure you're not changing the overall value. So to do that, let's actually um, float 32, okay, and divide this by 25, okay. And why am I dividing this by 25? I have 5 by 5, so I have 25 of these ones, so I'm dividing each one of those by 25. So if I run this again, let's run this one more time. Now you can actually see my kernel is nothing but 1 divided by 25, a 5 by 5 grid. So 0.04, 0.04, 0.04 throughout. Okay, so this is our kernel. If I open this, you can see it much better. Okay, there you go. So this is just, again, there are many ways. We can also define a Gaussian kernel if you're actually curious. Let's define the same Gaussian kernel we had before. So this is np.array. So we are defining an array. And our array is what? 1 over 16 1 over 8, I believe, and then 1 over 16, 1 over 16, and so that's the first. And then let's do 1 over 8, and then comes 1 over 4, which is the central pixel, I mean, of the kernel, and 1 over 8, and let's see, one more final, 1 over 16, 1 over 8, and 1 over 16. Okay, so that should do. Just to make sure I haven't made any mistake, let's go ahead and run this. Okay, there you go. So our Gaussian kernel is a 3 by 3 kernel of values 0.065. Again, let me open this so you can see. So the central value is the highest value, and then these are the medium values, and these are all the lowest values. So this almost, as you can visualize, 2D Gaussian kernel over there. Okay, so this is how easy it is to define your kernels. And again, you need to know what the kernels look like. For example, if you have Laplacian or Gabor or something else, you just need to define your kernels. In fact, there is a better way, right? I mean, in scipy.ndimage and OpenCV, there are various kernels that are already defined. All you need to do is import Gaussian and then just apply Gaussian. So you don't have to think about these kernels. But I'm just showing you how it is done. Now, to apply this convolution, to actually take this kernel and apply it onto your original image, which is nothing but I'm taking this kernel with values of 0.04, 0.04, and so on, and applying it onto my image that has values of right there, okay? Applying it to this grid. That's pretty much it. There are a couple of ways to do this. First, let's actually use OpenCV. uh, Import CV2. Okay, in OpenCV there is a function called filter 2D. Okay, so let's say my convolution using CV2 is nothing but CV2.filter 2D. Okay, so this is how you apply. Now I want to apply a filter on my image. Okay, and I'll input a depth of -1. Depth of -1, again, look at the documentation for filter 2D on OpenCV web page. Depth of -1, this is the output image will have the same depth as the source. That's what this means. If the input image is float 64, then the output image will also be float 64. Okay, so this is -1. And then what is my kernel? My kernel is kernel. That's how I defined it. Okay, so I'm going to apply this kernel onto my original image. And now what is my padding? Here it's called border type. Okay, so let's do our border type as CV2 border, all caps, constant. Okay, which means it's going to apply a constant border at the end. Okay, I believe if I don't give any default values, it's going to be a constant value of 0 padding. The other options, the only other option I think of is border underscore replicate. Okay, replicate means it replicates whatever the next value is in the grid of your images. I think we're all set. Let's go ahead and run it. And there you go, my conv using CV2. So after the convolution, these are the values, 0.042 and so on. Now, again, if you want, we can go ahead and have a look at this. So cv2.imshow, let's actually show original image is nothing but, what did I call image? Oh, I forgot my quotations there. Okay, there you go. And let's also show our let's say CV2 filter. Okay, and this would be conv using CV2, right? Conv using CV2. Okay, and do not forget CV2 dot wait key uppercase K 0, so we can close it whenever we want. CV2 dot destroy all windows. Okay, so let's go ahead and run this. And let me drag my input image. So this is my input image, noisy image, and this is the filtered image over there. Okay, as you can see, this is denoised a little bit, but also blurred. Okay, so that's the problem by applying these type of blur filters. It does denoise, but then the edges are blurred. So there are better algorithms, better filters out there that can take care of these edges. Okay, so this is as easy. Okay, we just defined our kernel, and then if you're curious, we can also apply Gaussian kernel. Okay, so let's go ahead and apply our Gaussian kernel and then run this. The values here should be different now. And Gaussian kernel, that's not bad. I mean, it did denoise, but we still see the edges to be slightly okay compared to the blur operation. Okay. So there you go. So this is how you can actually perform. And now let me go ahead and take 2 more minutes to show a couple other ways of actually applying this convolution. So if you don't like OpenCV, I don't know why you wouldn't, but if you don't like it, then another way of doing this is using the, again, there are two ways. I mean, there are two in under signal processing in scipy. There is convolve 2D. And scipy also has this, I think, under images. So from scipy.ndimage filters, you can import convolve. Again, many ways. All of these are doing exactly the same. Whether you use filter 2D or convolve 2D from scipy signal processing or convolve from scipy ND image filters, they all should do pretty much the same thing. And we can confirm that by looking at the output numbers over there. So let me go ahead and what are we doing? So let me go ahead and apply those so we can see. So now convolve using scipy. Uh, uh, using scipy, and how do we separate this? Let's call this signal. Okay, this would be convolve 2D. That's it. And what are we doing? Image, kernel, and mode equals to same, which means my output, keep it the same size as my input. That's what this is. Okay, so convolve 2D. Let's also apply kernel up here so we compare likes. Okay, now convolve using scipy, and this would be nd image and convolve, and let's do image kernel. And here again, if you look at this documentation, they don't have mode equals to same. They call this mode equals to constant, which is adding a constant value, and you can define what that value is. Our constant value, let's add it as 0 0.0. This is a floating value, so let's add it as 0 0.0. I think I typed everything okay. Let's go ahead and let's ignore the CV2 im show and all that stuff. Let's actually run these 3 lines so we can have a look at the numbers up there. We know how the image looks like. So convolve using, oh, there is an error, cannot import convolve. Sorry about that. Convolve. Okay. Now hopefully I seem to be doing the same mistake multiple times. Okay, there you go. Now let's go ahead and run this, and hopefully we should see all the values. Okay, if you look up here, you see convolve using CV2, using scipy ND image, using scipy signal. They're all floating 64 outputs, and they all have exactly the same values. Okay, so pick whatever you think works for you, and go ahead and work with that. Now, this is just a quick introduction to the convolution and how the convolution is applied and what it actually means. But in the next tutorial, let's actually talk about what is Gaussian kernel, and write a few lines of code just to understand this. And let's follow this trend and cover as many filters as we can in the next upcoming tutorials. Thank you very much for your attention. And again, as usual, I request you to please subscribe to my channel, as it definitely keeps me encouraged to teach you more about image processing.